All right, so yesterday we finished up talking about acid anhydrides. Today we'll try to get into esters a little bit. And anhydrides are pretty versatile. They're not as reactive as acid halides, but sometimes that's exactly what you want. So I showed you the example yesterday of making Tylenol in situations like that where you didn't want it to be too reactive. And anhydrides can be symmetric or non-symmetric, so those R groups can be the same or different. And let's do a little bit of practice. And we'll try to predict the reagents necessary to accomplish each of these transformations. So I'm just going to put in my skeleton network. And the nice thing with this is it's really, really similar to acid halides. So we'll put this one in. Do some R primes here. So now we made a tertiary alcohol. I'll do a ketone down here. And then I'll do a carboxylic acid over here. And we'll do both going to and from a carboxylic acid. All right, I think that's all of them. So let's just start with one of these. Does anybody remember how we can make an anhydride from yesterday's notes? Close. One option was to just heat the snot out of it. That was the 800 degrees Celsius reaction. But like I said, synthetically, that's not really done. It's only done for bulk scale of acetic anhydride. The other one is to simply deprotonate your acetic acid. So to deprotonate your acetic acid, first step, you need some sort of base to deprotonate it. That gets rid of this proton coming off there. Now it's a relatively good nucleophile, not the best, but what can you react it with to get the other half of the anhydride on? Not quite. You have to go with the king of electrophiles, the acid chloride, right? So acid chlorides, because they're so electrophilic, can actually react with very weak nucleophiles, and you can use this to get the other half of the anhydride on. All right, now let's think about going the opposite direction. What if you want to go from an anhydride just back to a carboxylic acid? Yeah, just water. Or you can treat it with sodium hydroxide followed by an acidic workup. Either one works, but these are easily cleaved by water. In fact, a lot of the tear gases that they use for crowd dispersion are actually anhydrides or acyl chlorides. Because they're so readily cleaved by water, they create a small amount of acid. It burns your mucous membranes in your eyes and in your lungs. That's why they're effective crowd dispersals. All right, what about going from an anhydride to an amide? Remember, this is just like with acid chlorides. So how do we get an amide with an acid chloride? Yeah, exactly, ammonia in excess. However, they show this in the textbook, and I don't really like this reaction, so I'm going to put, this is super slow. It's not a very good reaction to carry out, and like I said, there's a lot of other reagents available that do this much easier and much faster. All right, what about making an ester, the next one down? How did we do that with an acid halide? Yep, we need pyridine as a solvent, and then we need to get on that OR group. So that's probably going to be some sort of alcohol. So some sort of alcohol can be used to react with an anhydride, and you can get an ester that way. All right, how did we convert an acid halide to an aldehyde? We couldn't use LAH, it overshot. Yeah, the bulky LAH. Okay, so we'll fill that in. So this was the, Li, sorry, I've got it in the wrong spot here. LiAlOR 3H. That was our bulked up aluminum hydride, right? And that stops it at the aldehyde, prevents it from overshooting. All right, what about getting all the way to a tertiary alcohol? What would probably be the best for that? Grignard, exactly. So step one would be R prime MgX, followed by some sort of weak acid in order to protonate your alcohol. And then our last one that we had, again, we said that Grignards don't stop at the ketone, but we had a trick for stopping at the ketone. What reagent did we need? Gilman. That was the R2CuLi, and I'll put that as R prime. So like I said, understanding the acid halide one is one of the most important ones. The ones after that tend to be quite repetitive. So if you are reviewing, try to really focus in on the prior reaction map for acid halides. Make sense? Okay, now we've got to go into esters. Esters are really common intermediates in organic chemistry, and we've already discussed a bunch of ways to prepare them. And let's do a little bit of review. This is one we just covered recently where we can make an ester from an acid halide. What reagents did we need again? Alcohol and usually pyridine or some other tertiary amine. So that's one easy way to make, oops, sorry, that should be an OR, not an OH. So that's one easy way to make an ester. Let's do it another way. Again, this is going to be a review of what we just covered. I'm actually going to change this so it's color-coded. Same sort of reaction conditions apply for anhydrides. So you can do ROH and pyridine. Your alcohol and pyridine works well for either of these transformations. They're both electrophilic enough. All right, now we've got to do some review going back. Oops. Now we're going to try going from a ketone to an ester. Does anybody remember how we accomplished that? Yep, our peroxy acid, RCO3H. This was a Baeyer-Villiger oxidation where we inserted an oxygen in between the carbonyl-carbon bond. And it's important to remember which group shifts. So if your R group is a hydrogen, you actually make a carboxylic acid, not an ester. So understanding shift priorities is important. All right, the fourth one we have is with carboxylic acids. We can convert a carboxylic acid to an ester actually two different ways. So I'm just going to show these both. Oops, it should be OR. The first one was under basic conditions, and for basic conditions, what you need is first to deprotonate our alcohol, or sorry, our carboxylic acid with a base like sodium hydroxide. And then two, you need to react it with some sort of alkyl halide. And if we think about this alkyl halide, what sort of reaction do you think it's going to be? Do you think it's going to be SN1 or SN2? Yeah, probably SN2. In which case, should this R group be bulky or non-bulky? Yeah, so it should be unhindered. Meaning it should be a primary or a methyl group. Ideally, it won't work very well if it's tertiary. SN2 reactions just don't favor that. All right, for acidic conditions, we actually saw this previously as well. And this one's actually more common than the one right above because alkyl halides tend to cause cancer. The easier method to convert a carboxylic acid to an ester is treat it with strong catalytic acid and alcohol. In fact, this is how they make biodiesel. With biodiesel, you start out with typically a triglyceride fat, and you do this Fischer esterification, break the triglyceride into 3 different ester groups, and then you can burn that in a combustion engine. Why do you think normal triglycerides don't work well for cars? Does anybody know? Think about what happens to fat when it gets cold. Solidifies. So there's a lot of heat problems. If it's too cold, you can't run a diesel car off of pure fat, so you actually have to break it up into smaller esters. Those tend to be liquid at much, much lower temperatures, and you can use them in a biodiesel car. So that's one of the reasons why they do this for biodiesel, is to alleviate the temperature problem. All right, so those are the review reactions for making esters. I don't think we've covered any more. Now we need to look at the reactions of esters. And the first one is acid hydrolysis. And with acid hydrolysis, you can start out with an ester. You can treat this with water under acidic conditions. And I'm just going to put catalytic acid. And you can convert this to a carboxylic acid plus an alcohol. And if you notice, I've got equilibrium arrows here because it can go either direction. In fact, we just talked about this reverse reaction going from a carboxylic acid to an ester right above this. So then the question is, well, how can we favor going from the ester to the carboxylic acid, meaning going this direction? What could we do as a trick? Yeah, flood it with water, right? So one option is to flood with water to favor products. There's also another trick you can do, not on the starting material side. Yeah, take out some of the product. So remove alcohol to favor products. It really depends on the situation, but sometimes if you're kicking off a low boiling point alcohol, you can actually just distill it off as this is going and drive the reaction to completion. Does that make sense? Either of these are just manipulating Le Chatelier's principle. All right, second one is base hydrolysis. And we're actually going to do this in one of our labs. And with base hydrolysis, you're going to take an ester. You're going to slam it with a lot of strong base, typically sodium hydroxide or potassium hydroxide because it's cheap. And then in the end, you need to reprotonate your acid because you're under basic conditions, so you do a second step with strong acid. So you can convert an ester to an acid that way. I did want to show you the example of this in action. This isn't the most beautiful drawing, but you get the idea. What's that? Is it a tuba? Not quite. This is fat. This is just a triglyceride. And if you take a fat, right, and you treat this with strong sodium hydroxide, you're going to pop off each of these esters, right? Like that. What you're going to do in the end, you're going to make one chunk. This is glycerol. And for your other chunk, after you do the saponification, you're going to get 3 equivalents of a carboxylate salt. Does anybody know what this is really useful for? soap. This is what soap is usually made out of. So if you ever want to make soap at home, I'll actually post this on the website later. You can take a variety of different fat sources that are triglycerides. So a popular one lately is avocados. You can actually take the fat from avocados, treat it with strong base, pop it off, and make avocado soap. That's kind of a fun thing to do. Does anybody know why this makes a good soap? Yeah, if you look at this half, this is really, really polar. It's attracted to water. Versus the other half over here, the R group, is typically a really, really long hydrophobic group that traps grease, right? So if you've got a molecule that's both hydrophobic and hydrophilic, it's amphiphilic. That means it's really good at dissolving greasy compounds and getting them into water, right? So that's why I like showing this reaction, is it's something you can do at home. One thing I will say is you have to be very careful at home. If you add in too much sodium hydroxide and don't let your soap cure, meaning sit out for a few days, and you wash your hands with it, you're going to be washing your hands with excess sodium hydroxide, which is never a good idea. So saponification is a fun process. All right, there's also one more that you've actually already done for a pod. This is transesterification. It's very similar to the acid-catalyzed Fischer esterification that we saw before. But in this one, you're going to take an ester, react this with a second alcohol, so I'll call that R prime OH and keep it blue. Treat this with catalytic acid. When you do this, you can change one ester into another ester in your leaving group. In this case, it's going to be the alcohol that used to be on there. You can use the same tricks with Le Chatelier's principle that we talked about with the Fischer esterification. It just depends on the boiling point of your product alcohol. Sometimes you can distill it off and actually drive the product to completion, or you can just flood it with the desired alcohol and push it that way. So either end of the equation can drive the equilibrium. Does that make sense? And like I said, this is really popular for making biodiesel. Typically, the alcohol that you put in for biodiesel is methanol, and you can cleave that triglyceride and make a bunch of methyl esters that way. All right, there's a few more. And this is aminolysis. And this is a terrible idea, but I'm going to show it anyways because you might see it once in a while. And that's where you take an ester and your amine, and convert this to an amide. The problem is this is really slow. I don't know of any chemist in their right mind that would choose this as a suitable synthetic route. However, it can occur. It just takes a long, long time. Does anybody know why it's so slow? This is a bad electrophile. If you want this reaction to work, typically you want to choose a better electrophile like an acid chloride because those are way more electrophilic. All right, next one we've got is reduction. And reduction is fairly common with esters, so I wanted to show that. And we'll do review of second term chemistry. How can I go about making a primary alcohol from an ester? So with aldehydes and ketones, we could use NaBH4. With carboxylic acids and esters, we needed to amp it up. It means we need LAH. And we need this in excess, and we need to protonate it at the end. So we typically have some sort of alcohol or weak acid at the end. And it's important to remember that during this reaction, you actually go through an intermediate that's an aldehyde. this is a good electrophile. And you can't stop here. With LAH. But again, I'm sure you're seeing a theme. What can we do to fix this? Make it bulky, exactly. So unfortunately, you can't use the same bulky aluminum hydride reagent. That simply won't work with esters. It's too bulky. So we're kind of running into this Goldilocks problem. Are you guys familiar with Goldilocks? I said that last year and got blank stares. So with Goldilocks, right, she was trying to get the porridge that wasn't too hot, wasn't too cold. So they had to find this in-between reagent that wasn't too bulky and wasn't not bulky enough. And they came up with a special one. Close. So special reducing agent. It looks, oh man, where'd I put it? Right here. Looks like this. This is one of the more common ones. So it's got an aluminum with these two alkyl groups coming off. What are these called? They're not isopropyl. Isobutyl. So what this is called is diisobutyl aluminum hydride. This is kind of a mouthful. So what most chemists refer to this as is DIBAL or dibal. And then sometimes you see the H afterwards, sometimes you don't. It's kind of an assumed H. So sometimes people will write it as dibal H or just dibal. They're essentially the same thing. Does that make sense? Yeah, I think there's a sapling problem with this. And so the nice thing with this reagent is you can stop at that aldehyde. So let's take an example. If you've got an ester, you've got to choose your Goldilocks reagent. That's the dibal H. That's step one. And then step two, again, you need that weak acid to protonate things. And you can stop at the aldehyde. There are a handful of other aluminum hydride reducing agents that are similar to this, but like I said, you're trying to find that middle ground between being too bulky and not bulky enough. Does that make sense? All right. The last one that we need to know is reactions with the Grignard reagent. And this is one that students habitually miss on exams and quizzes, is they say, all right, if I've got a Grignard reagent and I've got an ester, can't I just stop at the ketone? No, students do that all the time on quizzes and exams. Again, the problem is this is more electrophilic. Than the starting material, meaning you can't stop here. So the reality is you do go through this in the process, but quite often you're going to overshoot. So let me make this step one. And then step two, you need to protonate it. So when all is said and done, you're going to end up making a tertiary alcohol, not a ketone. There are workarounds to getting to the ketone. So for example, maybe you do absolutely need to get to the ketone. What you could do, theoretically, is maybe convert your ester to a carboxylic acid, convert that carboxylic acid to an acid halide, and then react it with the Gilman reagent. Or you could take your ester, reduce it to an alcohol, oxidize it up to an aldehyde, add in a Grignard reagent, and then reoxidize it again. It's kind of a choose your own adventure sometimes, but Grignard reagents always overshoot with esters. I think somebody asked me last year too if you can do this with the Gilman reagent and stop at the ketone. I don't believe that you can because esters tend to be fairly bulky and not as electrophilic. So you can't really use the Gilman reagent, at least to my knowledge. All right, so we've got one more reaction map, and then I might let you out early so you can enjoy the sun. And you can probably tell the reaction maps are very repetitive. So we've got our ester in the middle, got a carboxylic acid here. Got our tertiary alcohol. Got our aldehyde. Got our primary alcohol. Then over here, I'm going to do a second equivalent of acid. Sorry. And then down here, I'll do another equivalent of ester, and then we've got a ton of reaction arrows we need to fill in. So I'm just going to get all these reaction arrows filled in here, and then we'll start completing our map. All right, so for example, let's just pick this one in the top right-hand corner. What were the two ways of converting an ester to an or to an acid? Yeah, so we can do acid and water. All right, that was one method we could do. That's an easy one. Alternatively, you could just write H3O+. Second one was sodium hydroxide, followed by strong acid. That was the soap making mechanism that I kind of showed you before, or similar to soap making. What about making a tertiary alcohol? Grignard reagent. That's the one that overshoots all the time. So this would be RMGX followed by acid. What about if we want to go to an alcohol? We'll skip the aldehyde one right now. LAH. In excess, followed by water workup. All right, what if we want to stop at the aldehyde and not overshoot to the alcohol? Dibal. That was DIBAL. And I normally show it as dibal H, so you remember that there's a hydride there, followed by some sort of protonation with water or weak acid. All right, how do we go from one ester to another ester? We need acid, and then our separate alcohol, right? So that was our transesterification, going from one ester to another. All right, and then conversely, going from a carboxylic acid to an ester, so we're going the forward direction. We've got a few different ways. First way was with our acid and our alcohol. That was the Fischer esterification. The second one, less common, but still doable, is sodium hydroxide. Deprotonate your carboxylic acid and then do an SN2 reaction with it. So that works. And then if you really want to take a roundabout way, you can always convert to the king of electrophiles, so convert it to the acid halide. And then once you're at your acid halide, then convert it to an ester using your alcohol and pyridine. What I always remind students is if you're ever stuck in a synthesis problem and you're not quite sure how to get where you're going, it's always safe to convert it to an acid halide because that's the most versatile intermediate you have from this chapter. So if you are in a pinch, like with this one down here, we converted it to an acid halide and then converted the acid halide to an ester. Make sense? All right, so next week when we come back in, we're going to look at amides and nitriles, and we'll probably have a full day of synthesis in between. I would try to get a jump start on sapling this weekend, though, because it'll sneak up on you.